Okay, hello everyone. Can you hear my voice and see my screen?
Yes, sir.
Okay. All right. So let's start from where we left last time. Um, last time we left at this chi-square distribution, and I asked this simple question that if x follows normal 0, 1, what is the PDF of x square? And it turns out that it's going to be chi-square with 1 degrees of freedom. Now, after that, there was a question that what if it is not x square? What if it is a some other function? Like what if it is x cube or x to the power 4? How do you find probability distribution of such things? So let us begin today's discussion with that, which is probability distribution of functions of random variables. Okay. So let's start with an example. So let x follows exponential lambda. Um, Find probability distribution of some function of x. So you want to find the probability distribution of let's say log x. Whenever I write log, I mean ln of x. It's base e. So this is just an example. You can have any kind of question, like you can ask what is the probability distribution of x square, or what is the probability distribution of e to the power x. So something like that. So if you have a random variable, you can look at any function of that random variable. That function itself is going to be another random variable. So you can talk about that probability distribution of that random variable. So the answer follows basically two steps for any of this kind of problems. Actually, I think I have done briefly done one example um, in one of the tutorial sessions. I think there was a problem where you have some circuit and the power is I squared times R. The PDF of I was given, and I actually found the PDF of I squared. So anyway, so let's formalize that. The step one is that find the CDF, the cumulative distribution function of log x. So because in this question it's log x, I am going to find the CDF of log x. If it is something else, I will find CDF of that thing. And then step two is okay. So now if you know the CDF of a random variable, how do you figure out the PDF? Simply differentiate it. So differentiate the CDF and the PDF. Okay. Um, all right. So let us do that. Actually, sometimes, so let me write down another thing. Or personally, um, you can also find the MGF of that function of x, and from there you can guess the for example, we have log x, and it will be actually difficult to find MGF of log x. So we will go with the standard procedure, which is we will find the CDF of log x and then differentiate to find the to find the PDF of okay, differentiate the CDF to find the PDF of log x. Okay. All right. So how do we do this? First of all, the PDF of x follows exponential, right? So x follows exponential lambda, and PDF of x is given by fxx, which is lambda e to the power negative lambda x when x is positive. Okay. Now we want to find first we want to find CDF of log x. So let us define y is equal to log x. Okay, so notice that if x is exponential, then x is taking only positive values, right? X only taking positive values. But if you draw the graph of log x actually can go from negative infinity to positive infinity. So log x goes from negative infinity to positive infinity. Okay, so this is an observation that y is actually taking values between negative infinity to positive infinity, whereas x was from 0 to infinity only. Anyway, now we want to find the CDF of y, right? So CDF of y is going to be fyy, that is a probability of y less than equal to y, which is probability of log x less than equal to y, and that is equivalent to probability of x less than equal to e to the power y. Basically, I am taking e to the power on the both sides, so you get you find something like that. Actually, this is the only step which will change from problem to problem. So let me put a comment here. For different problems, you will have different calculation there. That is the only step where the problem changes. For example, if we had so y is equal to x square. So suppose you want to find a PDF of x square, right? So at this step, you would have say like y less than equal to y. That is so probability y less than equal to y. That is going to be equivalent to probability x square less than equal to y, and which is probability negative square root of y less than equal to x less than equal to square root of y. Okay. So depending on different functions, you will have a different scenario at this step. So that is the step where it changes. Notice that when I was writing x square less than y, I also wrote negative square root of y less than x less than y, not only just x less than square root of y. So you have to be careful about those steps. Okay. But anyway, so in our case, we have x less than equal to e to the power y, and that probability is simply given by integration 0 to e to the power y, because we are going to put the PDF of x here. Now, essentially the point is that the problem was in terms of y. The problem was in terms of y, which is log x. Now I transformed it back to the problem about x, because why? Because we know the PDF of x, right? So we are going to use that. So you integrate the PDF of x, which is lambda e to the power negative lambda x dx, right? And integration is from 0 to e to the power y. Why is it from 0 to e to the power y? Because the PDF of x starts from 0 only. It doesn't start from negative infinity. Okay, now if you finish the integration, which is e to the power negative lambda x 0 to e to the power y, and that is going to be 1 minus e to the power negative lambda e to the power y. Okay, and for negative infinity less than y less than infinity. Okay, so y takes values between negative infinity and infinity. So we found the CDF, and then the step 2 is to find the PDF. So the PDF of y is simply by differentiating the CDF. So fx, sorry, fyy, little f y y, which is the derivative of the CDF. If I differentiate this thing, I get e to the power negative lambda e to the power y, and then differentiate that, I get lambda e to the power y. Okay. So that negative negative cancels after the differentiation. Anyway, so that's how we find the PDF of this y, right? And that's it. This is the end of the problem, because you wanted to find the PDF of this y, which is log x. Okay. So for any such function, so this was just an example with exponential distribution and log x, but if you have different examples, say like chi-square distribution with the x square, something like that, you can follow the exact same procedure and you can figure out the PDF of this function of random variables. Okay. So is there any question about this first example? All right. Okay, so let's move to the next topic. This is not a topic. This is some sort of observation, which is um, scaling and shifting of normal distribution. Suppose, so let x follows normal 0 1. I'm giving this example with normal 0 1, but it doesn't have to be with normal 0 1. It could be normal mu sigma square, but I just want to give an example. And suppose y is equal to a plus bx, okay, and a and b are some constants, okay, so a b are some constants. Say like y is equal to 2 plus 2 minus 3x, something like that. Now what we want to do, we want to find we want to find the PDF of y, or actually let's not write the PDF. We want to find the distribution of y. Okay. So x is a random variable, obviously y is a random variable, y is some function of x. Now you can obviously follow the previous technique. Previous technique means this y is some function of x, right? So you can try to find the CDF of y, which is a plus bx, and then differentiate that to get the PDF of y. That is definitely possible. I'm going to do another technique here, which is via the MGF. That's why I wrote occasionally you can find the MGF. So I'm going to find the MGF of y, okay, and we will conclude from there. So we shall find the MGF of y. Okay. So how do you find the MGF of y? Phi y t, which is expectation of e to the power t times a plus bx, which is expectation of e to the power at times e to the power btx. Okay. Now, if you look at this thing, you will see that this guy is just a constant. This doesn't depend on x, right? This doesn't depend on x. Now, if something doesn't depend on x, you can pull that outside of the expectation. We have learned this before. So you can pull it outside of the expectation. We see e to the power at, and then expectation of e to the power btx. Okay. Now, what is the expectation of e to the power btx? Okay. So let's recall something, that MGF of x, right? So MGF of x, which is normal 0, 1, x is normal 0, 1, is simply e to the power 1 half t square. Okay, and that is nothing but expectation of e to the power tx. So essentially, expectation of e to the power tx is 1 half t square. And now instead of writing t, if I write p, it will be 1 half p square. So basically, you write whatever, you will get 1 half square of that. So I have btx here. So this is going to be e to the power at times e to the power 1 half b square t square, right? Which is, if we write it in this way, which is e to the power at plus 1 half of b square t square, right? Can you recognize this MGF? Can anyone respond? So what is the MGF of like which probability distribution has this MGF?
Normal distribution.
Normal distribution.
A and B square.
Yes, so this is actually MGF of another normal distribution. If I write that down, so basically MGF of normal mu sigma square is e to the power mu t plus 1 half sigma square t square, right? And if you compare that, it looks exactly like that. It would be 80 plus 1 half b square t square. So essentially, this would imply that this y follows normal distribution a b square. Okay. So by the way, what did I say? Scaling and shifting. So scaling and shifting is actually this one. So this b is the scaling factor. And a is the shifting factor. So if you shift and scale a normal distribution, you get back another normal distribution based on the shift and scale. Okay. So any question about this example here? Now let me write down something. You can check. That if suppose x follows a normal mu sigma square, then if you define a new random variable, which is, let's say, x minus mu divided by sigma, then that will follow a normal 0, 1. Okay, exactly the same technique. If you follow the same technique as ever, so you start with x, you define a new random variable y is equal to negative mu over sigma plus 1 over sigma x, and things like that. So if you calculate the MGF of y, you will find that is going to be exactly the same as MGF of normal 0, 1. Okay, and this is actually a very important fact, and we'll be using all of these facts in the statistics class, which is starting next week. All right. Next thing is about again normal distribution, which says that. Okay, so this is about sum of independent normal distribution. In the previous lecture, we have seen that the sum of the squares of normal distribution, right? So sum of the squares of normal distribution follows chi-square distribution. Sum of the squares of normal 0, 1 follows chi-square. But if I don't take square, if I just simply take the sum of the normal distribution, that is actually more elementary question to ask. What is the sum of independent normal distribution? Okay. So suppose we have this exercise. Suppose this exercise follows independently and identically distributed normal, let's say mu sigma square. Okay. So each xi is normal mu sigma square independently for I is equal to 1 to up to n. Now we want to find, so let us define y is equal to x1 plus x2 plus dot dot up to xn. Okay, and we want to find, so we would like to find the distribution of y. Okay. So how do you do that? It's very simple. So if we will take the MGF path. Okay, so MGF of y, which is phi y t, that is expectation of e to the power ty, which is expectation of, and we have seen this trick 1,000 times before. So t x1 plus x2 plus xn, and using the independence we can split this expectation. We can write this as expectation of t e to the power t x1 times expectation of e to the power t x2, so on, expectation of e to the power t xn. Okay. Now expectation of each of these e to the power t xi. So you so each of these xi's are normal mu sigma square, right? So therefore, the MGF of each of these xi's is going to be e to the power mu t plus 1/2 sigma square t square, right? Which is expectation of e to the power t xi. So expectation of e to the power t xi for any I is e to the power mu t plus 1/2 sigma square t square. And essentially you are taking product of n of those, so it is essentially going to be e to the power n mu t plus 1/2 n sigma square t square, right? And that tells you that this y follows normal distribution with mean n mu and variance n sigma square. So if you add up n many normal distributions, that is also going to be normal distribution with mean n mu and variance n sigma square. Okay. Again, the same technique. I am just using MGF and concluding that. Now, okay. Now, if you combine this two-stirred equation with that this thing, right? We will see some interesting fact here. So here, what I said, from the scaling and shifting of normal distribution, I told you to check that. You can check it later. But if you have a normal distribution mu sigma square, and if you define a new random variable which is x minus the mean divided by the standard deviation, then you can prove that it will follow normal zero. And the proof is exactly same as this scaling and shifting, because essentially what you are doing here, you are doing the scaling and shifting of this normal. You are scaling by 1 over sigma, shifting by negative mu over sigma. Now if I apply that fact, what I see here is actually kind of amazing. It says that this y minus n mu divided by square root of this variance, right? So let's look at that again. It says that x minus mu divided by square root of the variance. So if variance is sigma square divided by sigma, that will follow normal zero one. So here y is following n mu and variance n sigma square. So if I take this, if I divide by the square root of the variance, which is sigma square root of n, this will have exactly normal zero one distribution, right? In other words, so what is y? Y is summation xi minus n mu divided by sigma square root of n. This is exactly normal zero one. Does this expression remind you of something? The summation xi minus n mu divided by sigma square root.
Yes, sir, that is CLT.
Okay, so it looks like CLT, but that's not exactly the case. Okay, so let me write down a word here. This is not the proof of CLT. Why? This is not a proof of CLT, because the remarkable difference between CLT and this statement here is that because in CLT, we have the summation xi I is equal to 1 to n minus n mu divided by sigma square root of n is approximately, okay, is approximately normal 0 1, okay, for, this is the keyword, for any sequence of any, so this is the important clause here, any sequence of IID variables xi each having mean, each having mean mu and variance sigma square. Okay, so why? So let me draw the difference once again. In this blue box statement, this statement is about sum of normal distributions only, right? So if you look at the beginning, right, I started from xi following normal mu sigma square. So all of these xi's are IID normal mu sigma square, right? And then at the final blue box, we have seen that the summation xi minus n mu over sigma square root of n is exactly normal 0 1. It is not approximately, it is exactly normal 0 1. If you begin with the normal distribution itself, so the moral of the story is that if you begin with the normal distribution itself, each of xi is a normal distribution, then this summation xi minus n mu over sigma square root of n is exactly normal 0 1. It is not approximately, it is exactly normal 0 1. But power of CLT is something else. CLT says that you do not have to start with the normal distribution. You can start with any sequence of independent random variables. Then this summation xi minus n mu over sigma square root of n will be approximately normal to 1. So if you do not start with normal distribution, that's okay. This quantity summation xi minus n mu over sigma square root of n, it will be approximately normal 0, 1. It won't be exactly normal 0, 1. But if you start with normal 0 or normal mu sigma square, then this will be exactly normal 0, 1. Okay, makes sense, right? Which which is not a contradiction, because obviously if you start from normal, you remain at normal. If you start from something else, you do not expect that it is going to be normal. It will be approximately normal. So that is the point here. Okay. Any question about these two statements that I made here? Okay. So essentially, I think this is all that I wanted to say about in the probability section. From the next week onwards, I will start the statistics part, and in the remaining time, you may ask me any question, or let me open up my Python program. Okay, can you see the screen now, the spider Python thing?
Yes, sir.
Okay.
Yes, sir.
Let me increase the font a little bit. Okay. All right, so let's see if it is working. Okay, it's working. So I'll be writing comments after this hash sign. Comment. Is this visible? What I wrote here? The ink is.
Yes, yes.
Yes, sir.
So whatever I write after the hash sign is a comment. So basically, what I'm going to do now, I'm going to do some about the weak law of large number. And maybe if I get time, I can do some CLT stuff also. Okay. So how does it work in Python? So in Python, there are already some pre-built values, which means you do not need to write so much of programs. There are already some pre-built functions. We can actually simply call them. We can simply import those modules and start programming. So I'm going to import the module called NumPy. So I just write import NumPy as NP. This as NP is an auxiliary statement. You do not have to write this down. Let me explain what this as NP means. So essentially, I have successfully imported the module NumPy. in my console, means so I'm using this console called like 1s. This is a Python programming console where I'm writing this program, and in the console it is renamed as np. So which means whenever I type, whenever I call np, np, the program will call the module numpy. I can always like type numpy, but I just abbreviated it. So for this for this one, it is not that useful. But sometimes module names are like big, matplot, live.pyplot. You just assign an abbreviated name, and it will be easy to call. Actually, that is the thing. Anyway. So now I have this module np. It says that if I type np is a module numpy from it's located at some. It shows me actually the local folder location. If I go to this folder, I can actually find the program there. Anyway, now so this module contains many functionalities, right? So any module contains many functionalities. And we can check, we can find the list of say called, I mean I'm writing in very loosely, so if it's these are always not exactly functions, these are called objects, but just to illustrate, we can find the list of functions inside module by calling this directory module name. For example, if I just type directory of numpy, which is np now, in my console it is now referred as np, I will see it contains like lot of functionalities. This np module contains lot of functionalities, and obviously we are not going to need all of that. I will be using this functionality in this module, which is called random. So that's because we are working with random variables. So this numpy contains actually a object called random, and if I call that object random, so I can call I can call any specific object. Okay. So I can call any specific object or function by typing the module name, module dot the function. Okay. So for example, if I type np dot random, it will tell me what this is. np.random is actually another module which is inside, which is sitting inside this numpy. Okay. And this np.random is basically a subfolder kind of thing. So np is the root folder, then np or numpy contains many of the subfolders. Each of the subfolders contains again a lot of other functionalities. So if you want to check what does this np and random contains, I can write np random under the directory, and it will show you all the objects and functions inside this directory np.random. So np.random contains a lot of functionalities. In fact, you can see now it contains in particular, for example, this binomial distribution, chi-square distribution, exponential distribution, gamma, like everything that we talked about, right? So I will start with, let's say, np random binomial. Okay, so np dot random dot binomial. np dot random dot binomial is a function. So in that random subfolder, there are a lot of functionalities, and one of that is binomial. Now, if I want to find the help of that, so what does this function do? In Python, we can do that. So let me write this down. So help np.random dot binomial. It will tell you the like usage of this function, or like how to use that. So it tells you if you excuse me. Okay. So I wrote np.random help np.random binomial. It tells you help on the built-in function binomial, and it tells you a documentation actually. So for example, if I can use this function to draw samples from a binomial distribution, and for example, it says that so this n is the number of trials, p is the probability of success, and so on, right? So we have talked about that in the lectures. So for example, if I write np random 9.1, it will draw. It will give you a random sample from a binomial 9.1. So for example, if I write this down, np random binomial, and suppose I want to draw a random sample from binomial distribution with parameters 12 and 2/3. 8. So this is some random number. If I run the function once again, it gives you a different number 10. So it will give you a random number from 0 to 12 according to the binomial distribution. And okay. So what is happening here? So essentially, it's like simulating the fact that you toss a coin 12 times. So this is like toss a coin 12 times, and suppose the probability of getting head of that coin is 2/3. Then np dot random dot binomial, binomial 12, 2/3. What it does, it gives you a sample from this binomial 12, 2/3. So essentially, when you call that function as np random 12, 2/3, the computer is like tossing inside it, tossing a coin 12 times with success probability 2/3, and it's counting the number of heads it obtained, and suppose in this case it obtained 7. So is it clear up to now? Who is there? Okay. Now, so there are say 63 students currently in this session. Now, suppose I ask every one of you to do this thing. So every one of you, I ask you to toss a coin 12 times and report me the number of heads you are getting. Okay. Suppose. So I'm going to simulate that. Suppose I ask every one in this class to toss a coin. Excuse me. Toss a coin 12 times and report me the number of heads. And everyone has the same coin. So every one has the same coin, or like similar coin. Probability of getting head is 2. So I give 63 coins to the 63 students in class, and I ask all of them to toss the coin 12 times. Each of them toss the coin 12 times, and report me the number of heads. Right now, everyone is going to get different number of heads. Right. So what I can do, I can run this simulation 63 times. Right. I will get 63 answers. You can also try to run a for loop. Right. We can run a for loop for 63 times. Okay. So for example, for in. There are many ways to initiate for loop, so I'm just using 63, and I'm going to print this call this function np.random animal with parameters 12 and 2/3. Let's see. So it give me like 63 outputs. So as if like all of you, all 63 students are tossing the coin 12 times, and everyone is reporting me the number of hits, right? So it gave me out 63 outputs. There's another way to do that actually in Python. You do not always have to run a for loop. In Python. Of running for loop, we can they call it vectorized. So which essentially means that I call this function np binomial 12 2/3, and if I specify the size here itself, so if I say size equal to 63, so it will give me 63 outputs. Okay, I do not have to always run for loop. Essentially, this kind of functionality is built in many of these modules, so it will avoid you running a for loop. You can just specify the size, and it will give you the 63 many outcomes. Okay, I can store the data in a variable. For example, I can store say like a is equal to that. It will not show me anything, but basically this 63 samples from binomial is stored in A. If I call A, then I will find that, so A contains all those 63 values, right? So if I'm not forgetting, I think length A gives me, yeah, so it gives me the number of data points inside A, which is 63. Okay. All right, so now also by the way, so let me tell you one more thing. So np random binomial 12 2/3 size 63, right? This gives me 63 sample values from same binomial distribution. So as I said, as if like all the 63 students are doing this experiment, like tossing a coin 12 times and reporting me the number of hits they get, right? But if I ask, okay, do that once more, obviously we're going to get different numbers, right? So for example, in the previous case, the first student got 11 hits, but when the same student is repeating the experiment, he got 8 hits. So like the fourth student got 8 hits in the previous trial, but when I asked to repeat the experiment again, which means I asked him to to toss the coin 12 times, he got 7 hits this time, right? So let me actually copy this and put it in that OneNote, and I will write you something there. All right. So essentially, what is this? This is these are like the values of x size, right? So this is what I was aiming to tell. So this is like my x1, okay? This guy is like my x5, right? This guy is x63, right? So all of these x size are actually random variable. That's what I just demonstrated, right? So if I repeat the same experiment again, if I ask all of you to repeat the experiment, you are going to get different outcomes, obviously, right? This big x size are the random variables, right? So each xi is a random variable, okay? Okay. And so let me actually type it. Each xi is a random variable, and this particular a set of numbers. I think I write it here. This particular set of numbers is just a specific what they call in probability is realization. Realization okay, it is just a specific realization of is x1, x2, and xn. So as I said that if I repeat the experiment, you will get different values for this xi, and each xi is following a binomial distribution, right? So each xi is following. So each of these xi's are IID binomial 12 to 3. Okay. Now, by the week of large numbers, right? So by hold on, let me erase that. So each of those are random and everything, so everything is fine. Now this 1 over n summation of xi is equal to 1 to 63 is also a random quantity. Is also a random quantity. I have just explained that, right? So because if I repeat the experiment, I will get different numbers, right? Now, but week of large number tells you, but that WLLN, excuse me, WLLN says that this summation of xi is equal to 1 to 63. Although this is a random number, right? So this is a random number, but this will be close enough to, okay, this will be close enough to expectation of this xi, or expectation of the binomial, which is, what is the expectation of this binomial? So this is binomial 12 to 3, right? So expectation is going to be 12 times 2 3, right? Which is 8. So this is going to be close to 8. So if you take the sum of these 63 numbers and divide by 63, you are going to get a random number for sure. You are going to get a random number because each of these xi's are randomly generated, but this will be close enough to 8 all the time. So let me try that. So here is my A that I generated, right? So A is the sequence of that 63 numbers, which is essentially, as I'm saying that it's like all of you did this experiment, right? Now, if I take the sum of A, right? So if I take NP sum of A and divide by 63, okay? So I get a number which is 7.85, something like that. This is close enough to 8, right? I mean, depending on whether it is close enough or not, depending on like your error threshold. But this is what my point is. You are going to get something which is close to that. But if I repeat the experiment once more, so let me generate it in the program itself. So np dot random, excuse me. Np dot sum. So I'm taking the sum of np dot random dot binomial binomial 12 comma 2/3, and I'm giving the size equal to 63. So I'm putting that whole program inside and divide that by 63. Okay, now this time it generated this 8.2. So essentially, if you run it every time, you're going to get different numbers, right? But all of those numbers are going to be close enough to 8. So this I'm repeating this thing with 63 samples, right? So this experiment is being repeated with 63 samples. So every time we will get a random number, but all of that is going to be close enough to 8. So here I'm repeating this with n is equal to 63. Obviously, if you increase n, you are going to get better and better approximation. By the way, that survey form is actually up. You can start taking the survey also. Anyway, but if I increase the sample size, so instead of 63, if I write as a 6300, 630, I'm going to get better approximation. So 7.89, and it will be more close to actually 8, something like that. So you will get random numbers this time, but it will be getting closer and closer to 8. Okay, so I am out of time today, so I will stop here. If you have any question about the simulation I did or anything about the lecture material today, you can ask. And also, so that thing is already online. Yeah, and you can start taking that survey.